This is my code for LAB05. Before I go too deep into it, I want to go over the calculations that we need to make beforehand. So our robot will need to travel in the shape of a triangle. We know that our side A is going to be 100 centimeters. Our beta angle is going to be 30 degrees plus the last digit of our 800 number, which in my case is 3. Knowing that we have a 90-degree angle as well, we can calculate alpha to be 57 degrees. We also can use cosine to find side C, which turns out to be 119.236, or roughly 119 degrees. With the Pythagorean theorem, we can find out side B, which is roughly 65 centimeters. Now these next two angles, probably the most important to what I'm doing. So we said that beta is going to be 33. Well, my first turn that I have to make, I have to turn 180 degrees minus beta. So in my case, that would be 147. Once I get past alpha here, I'll need to turn roughly 180 degrees minus alpha, which is going to be about 23 degrees. And of course, at the end, I'm going to go back to original position. I just need to go 90 degrees. Out of curiosity, I just wanted to see how many pulses it would take to make that 147 degree turn. And that was 1,184 approximately. For 123 degrees, approximately 991. And 90 degrees, it was approximately 725 pulses. So, some of our static variables here, I define my wheel diameter to be closer to 6.95. For this lab, I included my wheelbase of 14 centimeters. Counts per revolution was provided for us in the example at 1437. My first turn, second turn, third turn are, of course, 147, 123, and 90 degrees respectively. My distance 1, distance 2, and distance 3 are 100, 119, and 65 centimeters respectively. Difference, it's something I set to 0. That was just a difference in pulse count between left and right. Really probably don't need it for this. Can take it out. But I set my max speed to 254 and have a minimum speed of 30. But basically my max speed is to prevent when I'm incrementing, especially when I'm first starting out with the code, I don't want my motor to, for whatever reason, go way too fast and then potentially damage it. So I set a max speed of 254. And of course we have a button delay of 2 seconds. For my dynamic variables and ones that might change, most notably, I'm setting my motor pulses at 40 for the left and right motor. And my void setup, putting my serial baud rate at 9600. That's not needed for our submission, but it's what I had when I was it's what I have my demonstrator right here. We will sit here in the setup until we receive a button press, button A. Once button A has been pressed, we'll have a 2-second delay. And then we'll go through these functions here. First straightaway, which will be 100 centimeters. Once that's completed, we'll go to our first turn, 147 degrees. We'll then go to our second straightaway, which is 119. Our second turn, which is 123. Our third straightaway is 65 centimeters. And then our last turn, which is a 90-degree turn. Okay, so our first straightaway, we will reset the left and right encoder counts. Then we'll need the number of pulses to go distance 1, which in this case is going to be 100 centimeters. This function was provided for us in the example, and it's taking count for distance. It's taking the float value of the wheel diameter to count per revolutions and the distance, and it's what we're doing is this temp float is the result of the wheel diameter times pi divided by counts per revolution. We then take distance and divide it by that temp, and that's the new temp. And then we return the integer. And let's see, here we are. Once we have that, we can determine the number of pulses we need to go 100 centimeters. And here I'm printing this, again, not needed in the submission, but I'm printing the distance and the number of pulses needed. We then go into the let's go straight function. And this go straight function is going to be the same function that's going to be used for the second straightaway and the third straightaway as well. Let's go down and take a look at that. So this let's go straight. While this condition is true, basically, while the left or right encoders are less than the number of pulses that we need to go 100 centimeters, all this stuff will be happening. So we'll get the left and right encoder count, we'll set the left and right motor speeds. My only modification is if the left count plus the difference, which we set is 0, falls below the right count, I'm going to speed up or increment the left motor. Similarly, if the left count gets ahead of the right count, I'm going to decrease or decrement the left motor speed. What I'll be doing is I'll be printing what's going on. Tell the world what happened here. Again, not needing submission, but I'm telling the left and right motor pulse counts and the speeds. Once this is no longer true, we break out of this. We set our motor speeds to we stop the motors, setting them to 0. And then we go on to our next function within that loop, which is the first turn. So let me find that. So in the first turn, we reset our left and right motor counts. Then we need the number of pulses to make that turn, which first turn is going to be 147 degrees. So building off of the example that was provided for us, I made a count for turn. And what's happening here, I'll take the float of the wheel diameter, count per revolutions, the turn, which is the degree we have to turn, and then the base, which is going to be our wheel base. And here we're just basically doing a pulse calculation. I'm doing the angle divided by 360 times the base divided by wheel diameter times the count per revolution, and then I'm going to return an integer, even though it was a float. Let's see. First turn. Once I get the number of pulses that I need to go that angle, I will print all that, the turn and the degrees, and then we'll go into our let's turn function. And this let's turn function is going to be the same one used for the second turn and third turn. Let's turn. Okay. So again, while the left count is less, while the left encoder count is less than the number of pulses we need, or the negative right count is less than the negative pulses. And this is because it's going backwards and we're reading it as negative. So that's why I made it looks like it's negative. But here also we will get the left and right encoder counts. We will set the left and right speeds. The negative here again just means it's going the other direction. Okay, so if the absolute value of the left count plus the difference of 0 is less than the absolute value of the right count, we're going to increment the left motor, speed it up. And I say absolute value because again we're reading the value of the right. It looks negative, but it's just because it's going the other direction. Likewise, if the absolute value of the left count goes ahead of the right count, we will decrement the speed. And again, we'll tell the world what happened, which is just print the speed and the pulse count. Once this is no longer holding true, we will stop the motors and then go on to our next function within the void loop, which is go straight 119. Once that goes, we go to second turn, 23 degrees, then we go third straight, 65 degrees, and the third turn, 90 degrees. So basically, like we said, first straightaway, second straightaway, third straightaway, they're all the same except for the distances they have to travel. The first turn, second turn, third turn are all the same except for the angle they have to turn. However, third turn just has one extra thing added to it. Once it's done, it will stay where it's at until button A is pressed again. It won't go into the next function in the void loop until again once the button's pressed again. So here's our Romi robot. I've have a toothpick on the front. Just it'll help us with visualization when we're measuring. So I'm going to upload the code here. Uploading, and I've taken off the front caster. Still haven't weighted it since we're going so low. Higher speeds, I definitely need to do a better job weighting it. Okay, we're done uploading. So we'll show you what's the track here again. The yellow tape is 100 centimeters. That would be side A on the triangle. Let me set this up here a little bit better. The ruler here, that's the 0 mark, and it goes all the way to roughly about 65 centimeters. And that's side B on our triangle. We have here this diagonal piece of tape here. What it really is, it's roughly going to be 33 degrees or our beta. What I want to happen is when our robot goes, I'm hoping that when it turns, the toothpick will be in a similar direction as that tape. Then we'll have it travel. When we get to this piece of tape here, what I'm hoping is that the center of the robot will be over where those two pieces of tape meet. Then we'll want the robot to turn 123 degrees, somewhat go straight, go here, and then turn 90 degrees. So let's get ready to test this. Make sure everything is set up here. Okay, making sure everything's aligned. We're on this tape here. 1, 2. Here we go. So going pretty straight there. So far so good. Pretty good. You can see the robot, the wheel cutting on and off is left wheel cutting on and off just to keep the pulse similar to the right side. Okay. So pretty good on that turn. We're pretty straight. Okay, let's take some measurements here. Oops, kick the So we have our, this is 20 millimeters or 2 centimeters. So we can show you here. We are within that. So that's excellent results. Let's check over here. Looks like the wheel's pretty close, but not 100%. Looks like we are off maybe, looks like we're off 10 centimeters, sorry, 1 centimeter from that line. And then on this side, let's see, about 10 centimeters. So by the rubric on the lab, these are excellent results. So I'm pleased with the calculations we made and how the robot performed.